Okay, thank you very much for having me here. My name is Jongho Lee, and I'm from Seoul National University, so this is my hometown. This is how it feels, right? Waking up in the morning, driving 20 minutes, and then come to the conference, and you're here. So very different from other conferences that you have to travel for 10 hours. Oh, you guys travel 10 hours plus, right? Anyway, welcome to Seoul. Well, just in case you are really the hardcore conference person and you didn't plan anything in Seoul, I have a one page for you. The conference center, right in front of it, we have this Buddhist temple that you can just walk 3 minutes from here, and you can enjoy some of the cultures of Korea. If you go the other direction, there is a department store, and I love their, like desserts in their basement floor. So if you want to check out some desserts, foodies, that will be a good place to visit. And if you walk for about 10 minutes to the west, then there is a royal tomb, which is a nice garden type of setting. So just in case if you want to stretch your legs, these are the options around here. I have nothing to disclose. By the way, this talk will be more like an MR physics talk rather than anatomy talk. And maybe this is my last slide for the anatomy. I don't think I need to introduce these laminar structures of the cortex and cytoarchitecture, so well known. And what is less known is the myeloarchitecture of the brain. Now, there are studied, inspired by the Vogt study in 1919. And it provides you the parcellation of the brain, as you can see on the right, images of the brain. And in fact, this myeloarchitecture is more relevant to the in vivo human brain using MRI, because MR is not sensitive to the cytoarchitecture. Cell density doesn't really change the signal in MR, whereas there are multiple techniques that are sensitive to myelination or concentration of myelination. So the idea of this myeloarchitecture in vivo human MRI is acquiring the data is really translating this histological myeloarchitecture into MR myeloarchitecture so that you can have subject-wise myeloarchitecture map that may have a lot of information that are hidden inside of the brain. And the question may be, why do we care about the myelin? And if you look at your like high school knowledge, the myelin traditionally considered as the insulation for the axon and also induces saltatory conduction. If the study ended there, then again, imaging myelination may not be super excited except the parcellation of the brain. But recent studies has really revealed the breadth of information that are contained within the myelination or the myelin concentration in the brain. For example, developmental changes as well as aging shows large changes in the myelination, and neuroplasticity as well as learning has been shown to be related to the myelination directly. And many studies have shown that myelin are, can be considered as a structural basis for the function, and also it may deliver some of the information about the personal traits as well as some of the diseases are directly related to the myelination. So as the result, imaging myelin using MRI is a very powerful tool to understand the brain and brain characters. Again, this is really the MR physics lecture so that I can deliver what type of imaging options we have when you want to image the myelin. Roughly speaking, there are 4 different categories of the techniques that when we think about imaging myelin. The first one is the relaxometric techniques, like including T1 and T2. And this history of the imaging myelination using T1 and T2 really goes back to a long time ago. And even in 1994, there are attempts of the imaging the laminar structures of the visual cortex, where we know that there is a well-known structure of line of Chinari that has thick myelination. And that attempt has continued as we developed a better system like 3T as shown here. Again, by using T1 weighted image, people try to visualize this line of Chinari. And you can see that there is a slight hint of the high in signal intensity as visualized here. And at 3T, that took like 45 minutes of time so that you can convince the reviewer so that you can publish the paper. Well, if you go to the T2, the contrast reverses. So now in T2 weighted image, the line of Gennari, again, highly myelinated area in the primary visual cortex, has a lower signal intensity compared to the neighboring cortical region. And this suggests that myelin, if you have a high concentration of myelination in your cortex, you will see a shortening of the T1 as well as the shortening of T2. And that idea has been exploited in a few number of studies, including this one on the left, that shows the T1 weighted images of the marmoset brain at the resolution of 0.16 millimeter isotropic voxels. And the result, if you flatten the brain, the result is quite enjoyable in a sense that it makes sense. Primary visual cortex, primary motor, auditory, and sensory cortex all show highly myelinated cortex, whereas other areas show lower myelination level. What is not easy to translate this T1 weighted imaging into the human brain is the fact that if you have multi-channel coils, we do have these coil sensitivity biases. And also T1 transmit field also generates the biases as well. So you cannot really use T1 weighted imaging to visualize myelination in human brain. So you need to have this T1 map, which is often acquired with MP2 range technique. And the result on the right is really amazing in the sense that they use a 7T in the amazing resolution of 0.5 millimeter isotropic voxel size. Again, it took 56 minutes of scan time to acquire the whole brain. But the results are quite impressive in the sense that, yes, sorry about that. So you can see the decrease of the T1 values in motor and sensory area as well as primary visual area. And also you can generate these maps depending on which layer you want to investigate. So across these laminar structures, you can choose the level that you want to set the T1 map. And then based on that level, like you can say the 50% across my cortex, and then you can generate the images of that 50% location. And this T1 mapping has been partially validated by this with the comparison with the histology shown on the left, which labeled each area of the cortex as the mean gray level from the histology. And then what this particular study shows was the correlation of that mean gray level from histology with the T1 value of the same region. And you can see the moderate correlation with the correlation coefficient of 0.39, which is reasonably good considering that they are from the different subjects. And also one is histology and the other one is the MR measurement. And this again is one of the way of doing the validation that T1 values can deliver the information of the myelination. Another technique that was really popular in the field of neuroimaging is using the ratio, T1 over T2 ratio, as the surrogate biomarkers of the myelination. For the acquisition of the T1 weighted image, they use the MP range, and for the T2, they use the T2 space technology. And roughly in the resolution of 1 millimeter, you can acquire the data at 13 minutes of time. And the good thing about this ratio imaging is, as in highly myelinated cortex, we'll have higher T1 signal and lower T2 signal. If you divide the two, it kind of amplifies the contrast. It helps. A more important one is you are canceling out these coil sensitivity biases that are present in both of these images. And because you are canceling out these coil sensitivity biases, you are kind of improving the sensitivity or improving the artifacts from the coil sensitivity. still you are suffering from the B1 transmit biases that are inherent in two images, and they are different between the two images. A bit difficult to correct for it. Another disadvantage of this technique is it is not quantitative measures. That means if you acquire the data from one institute and you do it in another institute or different scanners, then you will see a similar pattern. But if you simply pick a value, the two will report a very dramatically different values depending on the scanner. So there are limitations about this technique. They improved their protocol in a sense that the original paper suggests to use 1 millimeter isotropic voxels, but if you think about the cortex, it's only like 2 millimeters to 4 millimeters thick. So doing the myeloarchitecture with 1 millimeter is a little bit challenging. So later on in the human connectome project protocol, they went for the 0.7 millimeter resolution, still taking 60 minutes of time. So I believe that's about a good compromise between the resolution and scan time. Using this protocol, they went one step further and developed this, multi-model cortical parcellation technology. So they not only use this Myelin map, but they combined the task as well as functional connectivity information, from which they were able to parcellate the brain, individual subject's brain in this level of, complexity. Well, all methods, or I should say that the reason why I present 4 different methods today is because there is no dominant one, because all of them has cons and pros. This T1 mapping or T1 over T2 imaging, it's really simple and sequence is available on any of your machines, and it provides a very efficient acquisition. So you can do high resolution scan, sub-millimeter as 15 minutes of time. That's really good thing. However, there are limitations of it as well. For example, T1 is not only dependent on myelination, but also dependent on iron concentration. And in the cortex, we have a large variations of iron concentration, so it becomes the complication factors. Another limitation about this T1 over T2 ratio imaging is the fact that if you look at the white matter and check their values, sometimes it can go really wrong. So this particular study utilized this corpus callosum and stained with lux of fast blue and do the correlation between the lux of fast blue and the T1 over T2 ratio. If this ratio is consistent, reports the myelination consistently across the white matter and gray matter, then even in the white matter, you may see the positive correlation, but the result is negatively correlated, which is a little bit worrisome. So don't use it for the white matter, stay with the gray matter, and you may need further validation of it as well. On the other hand, this Myelin water or Myelin water imaging and Myelin water fraction do report nice positive correlation with lux of fast blue, and that's the topic for next presentation, next imaging modality, which is Myelin water imaging. If you grab an MR physicist and ask what is the traditional way of doing the Myelin imaging, people will say Myelin water imaging. It goes back to 1994 when the first paper came out, and the physics behind it is quite impressive. When we measure the T2 decay from white matter, what we measured was not a single beautiful exponential decay, but rather the combination of 2 exponential decay, one decaying really fast and the other one decaying slowly. And what people discovered is the fast decaying signal in the T2 value of 20 millisecond comes from a different microstructure environment. So if you look at the myelin, we have this axonal space, you have extracellular space, but we also have another water space called myelin water space. There are the extracellular water as well as cytoplasmic water that are wrapped by this lipid bilayer. Because their gap is so tight, their T2 value is much shorter than axonal water. And we can measure it, and we can do multiple exponential feeding to our exponential decay curve, and then we can do this T2 distribution for each voxel. And then finally, we can measure this myelin water fraction as the ratio of this myelin water signal to the total water generating this myelin water fraction map. If you have high resolution, sorry about that. If you have high SNR, like if you scan a tissue and scan for 10 hours, then this myelin water fraction map will give you beautiful images, as you can see here, and showing a nice correlation with histology. However, when it comes to the in vivo, that's about the images that you can get. Because this multi-exponential fitting is ill-conditioned process, you don't get nice result. It's sensitive to the artifacts. As the result, despite the fact that this myelin water imaging is classical way of doing the myelin imaging, there's no study yet to utilize it for the myeloarchitecture of the cortex. And it's likely because of the limitation of the image processing and also the limitation of the SNR. So most of the most of the application of this technology was for the white matter using a large voxel size shown here. Having said that, MR physicist has been very diligent in developing new technology, and the recent paper in 2024 from Stanford shows that you can acquire this myelin water fraction map at the resolution of 0.66 millimeter in 15 minutes of scan time. So maybe next year you will see myeloarchitecture map from the myelin water imaging. We'll see. Another classical method of doing the myelin imaging is using MT, magnetization transfer. This technique also has a very complex physics behind it. So let me try to explain it. In this particular imaging, again, there are two different water pools that are different from the previous myelin water imaging. The first water pool is MR visible free water, and the second water pool is MR invisible bounded water from macromolecules. These are the hydrogen atoms that are, like tightly bonded by the macromolecule. So here, macromolecule, you can think about it as a myelin. And then there is always some magnetization transfer between the two pools, and our aim is to saturate this, macromolecule bounded water using off-resonance RF pulses, and then indirectly measure their concentration from this exchange of the magnetization between the two pools. And the measurement result is called MTR, so magnetization transfer rate. To acquire that value, you need two images, one without empty pulse, one with empty pulse. Well, the technique is sensitive to the macromolecule, so that's a good thing, as myelin is macromolecule. But it is also sensitive to other factors, including B1 inhomogeneity and T1, and the shape of the empty pulse. There are advanced MT methods that overcomes these limitations. So that means if you spend more time in acquiring the data, then you can have a better specificity to the myelination. And one example of using this MT saturation for the myeloarchitecture imaging is shown here. They use this MPM protocol. It's multi-parametric mapping protocol that acquires three different GRE, one with MT, the other without MT. And this protocol helps you acquire like 0.8 millimeter resolution in 19 minutes of scan time. And what is good about this one is it generates not only the MT saturated myelin images, it also provides you this R1 map, which is one of our T1 maps. So again, naturally you get T1 map image information. It also delivers this R2 star, which is magnetic susceptibility contrast. As you can see, they all show a pretty similar distribution of the myelin in the cortex. And also, if you choose in ROI and see how the profile changes from the surface of the cortex to the gray and white matter boundary, they also look pretty similar between R1 and MT, but a little bit different in R2 star, probably because of the biases of the iron concentration there. So if I summarize the pros and cons of the magnetization transfer imaging, it's one of the validated techniques with lots of clinical research done using the technique. There are advanced methods that overcomes the limitation of B1 plus and T1 and vendor dependency, but they all increase the scan time, so there are limitations as well. It is sensitive to the macromolecules and may not be specific to myelin, but roughly myelin is one of the important contributor there, so you can use it to a certain extent. Okay, let's move on to the last technique, which is magnetic susceptibility imaging technique. And this is no new technique for you. If you do fMRI contrast mechanism is the susceptibility effect of deoxyhemoglobin, right? As illustrated in this 1990 papers from Ogawa. The concentration changes of deoxyhemoglobin creates the field perturbation, which was, encoded in your T2 star weighted imaging. Well, deoxyhemoglobin is not the only source for the susceptibility. In the brain, we have two other sources. One is, of course, myelin. It's diamagnetic susceptibility source. While deoxyhemoglobin is paramagnetic susceptibility source, so they have different content, different sign. Another source of the susceptibility is iron, which is usually in the form of ferritin. It's a paramagnetic susceptibility source. So, if you think about the sign of the susceptibility, you can kind of think about that you can distinguish myelin from ferritin because they have different sign. And then technology has been developed to visualize this susceptibility using T2 star or R2 star, or using quantitative susceptibility mapping, which is called as QSM. And this is two examples of using T2 star on the left, or also using R2 star and QSM to generate these myelin maps in the cortex. Again, they show a very similar concentration, variations across the brain, although all of these will be biased by the ion concentration as well as blood vessels, also including the fiber orientation effect. Recently, we have developed another, advanced susceptibility imaging method. Again, the advantage, special advantage of this, susceptibility imaging is if you can really go to the high field and generate these high resolution images in a reasonable scan time. So in this particular technique, we acquired the data at 7T at the resolution of 0.65 millimeters in 8 minutes of scan time. The advance of this technique is the fact that we can separate this positive susceptibility from negative susceptibility, or diamagnetic susceptibility to the paramagnetic susceptibility. And the one that is shown here is really the diamagnetic susceptibility map roughly matches to the myelin map in the brain. Of course, you can see a lot of vessels there, so there are complications that needs to be overcome in the future, but there are the directions for it. When we did the correlation between the histology and this diamagnetic susceptibility map, it shows a pretty good correlation here. And also in the primary visual cortex, you see this line of Ginari bump in both of the results. And you can go further for the in vivo analysis of the cortical profile that shows the expected profile of the iron and myelin when you compare the paramagnetic and diamagnetic susceptibility images. So the summaries of this susceptibility imaging, they do provide contents of the myelin concentration, and it is really a SNR efficient technology, and you get the gain from the high field so that you can get to the high resolution data sets. However, there are complications from iron and other sources that needs further processing technology to remove them. The most exciting news of this year, at least from my perspective, is this result from France, where they used finally the 11.7 T for the human scanner. And look at their resolution. Now they can acquire the data at 0.19, 0.19, and 1 millimeter, and only 5 minutes of the scan time. Okay, still they are not doing the myelin imaging yet, but that can be the future to get these cortical profiles using the technology of susceptibility. Again, this is one slide that compares different technology, R1 map, T1 over T2 map, MT, and T2 star. They are all from different subjects, so you cannot really compare, and they are color-coded differently, so you cannot really compare one by one. But at least what you can see by glimpsing through the images is the fact that cortical myelination is really high in the primary motor, primary sensory, visual, auditory cortexes. and it's usually pretty low in insula, frontal, and prefrontal cortexes. Still, there are discrepancies found in the images. If you look at this empty location circled in green, they do show up nicely in R1, and it's okay in T1 over T2, but begin to disappear in MT and T2 star images. So we need more validation of the technology so that we can confirm which one is more sensitive or correctly convey the information. Some of the applications that I want to talk about, the first a direct application of these technology will be the brain parcellation. And you can do the whole brain parcellation, or you can focus on some of the small area like visual cortex and doing a detailed parcellation of the area. More applications will be more complicated studies like this one. You can use the Myelin images and looking at this association cortex, giving you faster cortical myelination over the adolescent period. If you have the resolution and if you have sensitivity to myelination, you can come to this kind of conclusion using the technology. Another one is the matching the structure and function or predicting, to see whether structure can predict the function by using Myelin imaging for the cortex as well as the MEG data. And they show some of the correlation between the myelin density or the R1 values as well as the MEG measurement. So now we have the technology, but they're not complete. So if you just see what we really want to have for this type of cortical myelin imaging or myeloarchitecture imaging, the important one is really the resolution. Cortex is only 2 to 4 millimeter wide. So if you want to get multiple layers from there, you really want to have like 0.3 millimeter isotropic fossils. Then you roughly have 6 layers within 2 millimeter. Well, if that resolution, motion will be a problem, so scan time needs to be limited, like maybe 5 minutes will be great. And you want to have one specific myelin-specific imaging technology that provides you high CNR and SNR. And these are the risks that I mentioned, and roughly the technologies that are available at hand. The first two technologies based on susceptibility, but they haven't shown to be used for the myeloarchitecture imaging yet, but they will, I believe. And the others are something that is available for you as the current technology. What do we need if we really want to do this right? Yes, 11.7 for everyone, maybe the right direction to go. Or we also want to have some of the more histological validation results, as we don't have much histology to compare with the in vivo result yet. So this is really my last slide. So if you are doing a lot of MRI, and if my presentation gave you the hint that maybe this can be used for your study, this is really the practical guidelines, how you can do the myelin imaging. If your protocol happen to have MPRH, T1, and fMRI, then sorry, you cannot really use the acquired data. But you can still change your protocol a little bit, maybe changing the MPRH to the MP2 range, 3 more minutes, you have T1 map. Now you can use it. Or you can do the susceptibility imaging, adding 5 more minutes to get the nice QSM result and more. And also you can do the T2 space for another 5-minute scan, you can get this ratio. If your MR physicist did a great job and add the susceptibility imaging or the MT imaging, then you're good to go. Try to use the more advanced one, not the old one, as the old technology tend to have complications. And try to get to higher resolution. As the cortex really thin, you need the resolution to see it well. If you're doing the MPM, that's great. You have 3 options to analyze the myelin. Now you have to choose which one to do it. My final take-home message is you really need to understand the technology before you use it. There are so many complications here, so there is nothing like single button, push button result that you can tell it as a myelin imaging. But again, this is one of the exciting new fields that may give you plenty of new information for your brain, for the understanding of the brain. With that, I want to thank my students at Seoul National University, who does a lot of great research on the topic of myelin imaging. And I want to thank you for coming to Seoul, and hope you enjoyed the Seoul for the rest of the conference. Thank you.
Thank you so much. So there was one of the comments, because it's a comment more than a question, and I just have to endorse it, which says, thank you very much for this wonderful talk, which is physics, but understandable for anatomists. And I think some of the questions that have been asked were answered in your latter slides, but how would you judge relaxometry if T2-weighted images aren't available? So for example, in clinical stroke MRI, but if you only have FLAIR images?
Well, there are studies using the FLAIR as instead of T2-weighted image, and they use like this ratio between T1 to FLAIR images. But my suggestion is, first you have to make sure that your FLAIR image has a thin slice. Many of the clinical FLAIR image has the slice thickness of several millimeters. If you have several millimeters, okay, don't do it. Because your cortex, again, will have less than one voxel. So it will be very difficult to use thick FLAIR slice imaging for the cortical myelination. And the other reason that I forgot to explain is the fact that myelin is really abundant in the white matter. So if you get the partial volume from white matter, then your signals are gone. Like it's really biased by the white matter myelination, not so much on the gray matter myelination. Hope that answers the question.
I'm sure. What is your recommended method for myelin mapping if we're using 7 Tesla in which transmitter inhomogeneity gets worse?
Right, at 7 Tesla, there are 2 options. The first one is using the T1 map. Again, using MP2 range, yes, you get reasonably good resolution, like 0.7 resolution or 8 resolution at the 10 plus minutes of scan time. Another one is going for the susceptibility imaging and chi-separation. There you get a higher resolution, but we haven't fully shown the myeloarchitecture using susceptibility imaging yet. Yeah, sorry about that. You can use the R2 star mapping and use it as a surrogate marker for the myelin. So yes, there is a technique, but not so much on the QSM side. So it's in work in progress, by the way.
Looking forward to that one then. So they're currently building the 14 Tesla MR scanner. Now, do you think that pushing resolution will improve our understanding of the brain?
Definitely yes. Yes, I want to have 14 Tesla for sure. So the thing is, we want to know this myeloarchitecture in a sense that we want to know it layer by layers. Like visual cortex, primary visual cortex, the line of generic, that's the input layer. And we want to know how thick or how much myelination is there in that layer, right? If you think about the layer-specific fMRI, we have a counterpart in the layer-specific myelin imaging. And if the output layer has more myelination, it probably have a very important meaning in neuroscience. Well, okay, I'm a physicist, so I cannot really tell. But I believe there are values in it.
So it will almost be looking down a microscope only, hopefully, only with a living person. I dream of that, that would be nice. Do you think the myelin architecture is more sensitive to function in cortex than in subcortical structures?
Subcortical structures, I don't have much comment on it. I think not many people have looked into the myelination in subcortical structures. So, or my knowledge on that topic is limited, so I cannot really comment.
Well, people just, normally they don't even look at myelination in the cortex, not even in post-mortem studies.
No.
Which is a pity. We underestimate its importance. So, one final question. Are there any studies that see how myeloid changes are related to cognition or disease?
Oh yeah, there are plenty of studies looking at this line of the studies.
And you're going to present the next.
Let me, if I have time. I think that, you may refer this paper, and they may give you the overview of the list. They do have the list of the papers referring to the disease-related and the cortical, cognition-related myelin concentrations. Yes. Okay. Thank you very much.